Hello everyone! In the past few months, I have been working on my first Beetleweight combat robot, called Tekkadan. As of now, the physical robot is not yet finished, but I would like to give an overview of the design and look at the CAD models. I will also be making progress videos of the building process in the future. In the beginning, before any designs were drawn out, I set out some requirements. The robot must have a spinner as its primary weapon, and it must be able to store at least 1.5 kilojoules at an angular velocity of about 900 radians per second, where bite could still be achieved. The archetype I decided to build was an undercutter. This was mostly due to experience with the archetype, as my Antweight Pure D was also an undercutter, but also due to many other factors, such as the ease to 3D print the entire chassis in one piece for strength and ease of assembly, good invertibility, and the ability to hit low wedges, as well as purely my own aesthetic preference. For the theme of the robot, I was inspired by a design that I worked on with a friend in the physics sandbox video game called Besiege. This Besiege combat robot was also called Tekkadan, and that's where our Beetleweight robot got its name and color scheme from. Now, let's look at the CAD design I made in Fusion 360 of the final version of Tekkadan. Okay, now we're in Fusion 360. Let's begin the breakdown. First, let us start with the weapon system. And obviously, the most important part of the weapon system is this disc. So this is a new disc I designed for Tekkadan. It's a single tooth asymmetrical design. It will be made out of 6mm AR500 abrasion resistant steel, which is a nice through hardened steel, and it will weigh approximately 431 grams. So that's 1/3 of a Beetleweight, basically. It's very hefty, it's a lot of weight, and that is because I wanted the requirement for relatively slow speed around 9,000-ish RPM. I want to get at least 1.5 kilojoules. And this spinner has quite a lot of moment of inertia because all of the mass is concentrated on the outside, and also because of how heavy it is. This is quite the heavy disc. What mounts it to the chassis is this central weapon shaft. So right here, this is a placeholder. I don't have actual CAD models of a lot of the parts here that are commercial because though they're complicated, it causes a lot of lag for the system, especially when I render. But this is supposed to be a quarter-size shoulder bolt, and it has a hardened shoulder which can act as the central weapon shaft for the weapon system. What holds the weapon in is an acorn nut on the other side, which attaches onto the bolt, and this also acts as the skid pad for the front weapon. And what allows this weapon to spin freely are weapon bearings. So we have 2 weapon bearings for a lot of extra stability. One weapon bearing will be situated inside of the disc in a hole. The other one will be in a commercial bearing block. So right up here, this is a commercially available bearing block with a screw pattern, which allows these screws, 8 screws on the bottom. These 8 screws, they will hold the weapon to the bearing block and to everything in between. And in between, we have a spacer. So this spacer here, let me find it. Spacer. This will be made of aluminum. It will provide the space needed so the weapon doesn't hit our drive belt for the weapon. And of course the weapon side pulley. So this pulley is made of aluminum. It's also a commercial off-the-shelf pulley. And that's connected to the belt, which is then connected to the motor side pulley, which is how the motor can deliver all of its power to the spinner. And you can see here, the pulleys actually have a slight reduction. This is 18 to 25, so it's 18 on the motor side and 25 on the spinner side, because the motor is actually going to spin at about 12,000-ish RPM. It's 1100 kV, or 1100 RPM per volt, and we're running 11.1 volt or 3S lithium polymer batteries at full charge. That's around 12.4 volts, and because there's the aerodynamic drag and friction and all of that, it's going to spin a little bit slower than theoretical. So with that and this gear reduction here, the spinner is going to be spinning at about 9,000 RPM, which is what we really want. Okay, that aside, we have the motor pulley, which mounts directly onto the can. So this is the motor pulley. It has some notches cut into it. This is designed to mount directly into the motor, because the motor itself will have little cooling ports on the bottom where the notches will fit right into. This motor here is just a placeholder, but this will be a 420 watt motor, and again it's 1100 kV. So in theory, with 420 watts and a theoretical energy of about 1.7 kilojoules, it's going to take a little bit more than 4 seconds, probably, accounting for some aerodynamic drag, to spin up to top speed. And yeah, that's the motor. Now let's talk about the chassis. So this is the unibody tub chassis that the entire robot is centered around. It will be 3D printed in one single component, actually like upside down. It'll be 3D printed like this, where it's flat to the printing bed. And this is what the entire robot is built around. As you can see, down here there's the hole for the shoulder bolt to go through. There's all the mounting holes for the top panel, the electronics bay to hold all of the electronics, such as the battery, speed controllers, the receiver, and also the 2 drive motors. We'll get to them later. But most importantly, what mounts onto these, I feel like, are the top panels. The top panels are consisted of 2 pieces, the front top panel here and the rear top panel here. The front top panel is actually very important because it's what the weapon motor actually mounts onto. As you can see, there's slightly larger screws here. Those are actually catted screws. Those are what attaches the motor to the top panel, and the top panel is then attached onto the chassis, which is what attaches this motor onto the robot. This is similar design to my Antweight Pure D, which also has a motor attached to the top panel. It allows for some extra give, a little bit of shock mounting per se for the motor. Makes it a little bit safer. And also, of course, the head of the shoulder bolt sits on top of the top panel. And then now let's get to the rear top panel. The rear top panel doesn't have as many features. It's mostly just a piece of armor. These top panels will also be 3D printed, of course, but they do actually mount both onto the chassis and also onto the wheel guards. So let's look at one of these wheel guards. Come on, Fusion load. Okay, here we go. Let's look at one of these wheel guards. So as you can see, some of the mounting holes go from the top panel, which helps with a little bit of extra stability and a little bit of extra integrity, I guess. But it's mainly mounted onto the chassis via also screws. We got a screw hole in the front, mounts into the chassis, and 2 here in the back, which mounts onto the back armor of the chassis. And these wheel guards are supposed to protect the wheels, obviously, from impact, also from enemy spinners. And they're also a piece of aesthetic element that added to make the robot look like a little bit bigger, and of course to cover up the exposed wheels. Alright, so those are the chassis elements. let's get to the drive. So as you saw in the chassis, we have mounting points for drive motors. And the choice of drive motor are these Fingertech Silver Spark motors. So these are standard Fingertech commercial off-the-shelf motors that you can buy. They're usually meant for combat robotics, and supposedly they're pretty durable. And the ones I ordered are 30-to-1 ratio, so they're going to be spinning quite fast with 11.1 volt power system. But that's good. We want a lot of mobility, and they're not going to have as much torque as, say, a 50-to-1, but since we're not a push bot, we don't need to push, we just need to get the spinner to the enemy. I think 30-to-1 is a good choice. And mounted onto that motor, of course, are the wheels. The wheels we have are also made from Fingertech. These are 2.25 inch foam wheels made of neoprene. They're very good at absorbing shock. They're not that grippy, but I hope to coat them with a little bit of silicone, which will improve the grip quite a lot. But they're not the best at taking hits, but that's why we have the wheel guards here. These are good at absorbing shock, so in case of a hard landing, it won't bend the motor shafts for drive. It won't bend the drive shafts, and it won't, shock the electronics too hard. That's all we really need for a robot like this, where it's going to be going in for impacts with the spinner. And yeah, those are foam wheels. They're going to be mounted onto the motor via also Fingertech twist hubs. However, I just didn't bother to CAD them. They're going to be there. They're pretty light, made of aluminum. And yeah, that is the drive system. This concludes the breakdown today. I hope you enjoyed watching this video. If you have any ideas, please feel free to leave a comment below. I will happily read over them and hopefully make Tekkadan a better robot. This is Peter with Team Embarrassing Engineering. See you next time.